Our planet, Earth, is in constant motion. It spins on its axis, creating day and night. It orbits the sun, bringing about the seasons. But there's more to this celestial dance than meets the eye. Earth's movements are not perfectly uniform. They change over vast stretches of time, influenced by the gravitational pull of the sun, moon, and other planets. These subtle variations are known as Milankovich cycles, named after the Serbian scientist who first described them. Milankovich cycles are like a slow cosmic clock, driving long-term changes in Earth's climate. They affect the amount of solar radiation our planet receives, influencing the advance and retreat of ice ages over millennia. Understanding these cycles is crucial for unraveling the complexities of Earth's climate history and predicting future trends. The consequences of these celestial variations are far-reaching. They impact the distribution of ice sheets, the rise and fall of sea levels, and the very ecosystems that support life on Earth. Let's delve deeper into the world of Milankovich cycles and explore how they shape our planet's climate destiny. Milutin Milanković was a Serbian mathematician, astronomer, climatologist, geophysicist, civil engineer, and popularizer of science. Born in the village of Dal, which was then part of the Austro-Hungarian Empire, later Yugoslavia, and now modern-day Croatia, Milanković showed an early aptitude for science and engineering. He studied engineering at the Technische Hochschule in Vienna, where he earned his doctorate in 1904 for theoretical research on concrete and the design of concrete structures. Milanković's career began as a construction engineer, but his true passion lay in applying his mathematical skills to broader scientific questions. In 1909, he became a professor of applied mathematics at the University of Belgrade, where he remained for 46 years. His most significant contributions were in the field of climatology, where he developed the theory of long-term climate changes driven by variations in Earth's orbit and axial tilt, now known as Milankovich cycles. He identified three primary cycles: eccentricity, axial tilt, and precession. His groundbreaking work, published in 1940, provided a framework for understanding the cyclical nature of Earth's climate. It revolutionized our understanding of ice ages, showing that they were not random events, but rather predictable outcomes of Earth's celestial dance. Though his theories were initially met with skepticism, they were later confirmed by geological evidence and became a cornerstone of modern climate science. The Earth's orbit around the Sun is not perfectly circular, but slightly elliptical. This ellipticity, known as eccentricity, varies over cycles of approximately 100,000 years. When eccentricity is high, the Earth's orbit is more elongated, resulting in significant differences in the distance between the Earth and the Sun at different points in the year. During periods of high eccentricity, the Earth receives significantly less solar radiation when it's farthest from the Sun. This reduced solar energy can contribute to cooler global temperatures and potentially initiate or intensify glacial periods. Conversely, low eccentricity, with a more circular orbit, leads to more consistent solar radiation throughout the year. Though eccentricity alone is not sufficient to trigger an ice age, it plays a crucial role in modulating the intensity of solar energy received by Earth. This variation in solar forcing, combined with other Milankovich cycles, can have a significant impact on long-term climate trends. The Earth spins on its axis, tilted at an angle known as obliquity or axial tilt. This tilt is responsible for the seasons we experience. Currently, Earth's axial tilt is about 23.5 degrees. However, this tilt is not constant. It oscillates between approximately 22.1 and 24.5 degrees over a cycle of around 41,000 years. When the axial tilt is greater, the poles receive more direct sunlight during their respective summers, leading to warmer temperatures. Conversely, winters become colder as the poles tilt further away from the sun. Changes in axial tilt primarily affect the intensity of seasons rather than the overall amount of solar radiation received by Earth. A smaller axial tilt results in milder seasons with cooler summers and warmer winters. This can contribute to the growth of ice sheets as less ice melts during the summer months. We covered the Earth's path and the tilt, but the story of tilt does not end here. Introducing the wobble. Imagine Earth as a spinning top slowly wobbling on its axis. This wobble, known as precession, is caused by the gravitational forces of the Sun and Moon acting upon Earth's equatorial bulge. Precession causes Earth's axis to trace out a circle in the sky over a period of approximately 26,000 years. This wobble affects the timing of the seasons relative to Earth's position in its orbit. Currently, Earth is closest to the Sun in January, known as perihelion, and farthest in July, called aphelion. However, due to precession, these positions will reverse over the next 13,000 years. This shift in the timing of the seasons can influence the severity of winters and summers in each hemisphere. While precession doesn't significantly alter the total amount of solar radiation received by Earth, it affects the distribution of that energy across the globe and throughout the year. The three Milankovich cycles, eccentricity, axial tilt, and precession, operate at different timescales ranging from tens of thousands to hundreds of thousands of years. Their combined effect is a complex interplay of subtle variations in solar radiation reaching Earth, leading to significant long-term climate fluctuations. When these cycles align in a way that reduces the amount of solar radiation reaching the northern hemisphere during summer, ice sheets can expand. This is because less solar energy means cooler summers, allowing snow and ice to accumulate year after year, eventually forming massive glaciers. These glacial periods can last for tens of thousands of years. Conversely, when the cycles align to increase solar radiation during the northern hemisphere summer, ice sheets retreat and the Earth experiences warmer interglacial periods like the one we are currently in. It's important to note that Milankovitch cycles alone do not fully explain the complexities of Earth's climate. Other factors such as volcanic eruptions, ocean currents, and atmospheric composition also play significant roles. The study of past climate records, such as ice cores and sediment layers, confirms that Milankovitch cycles have been the primary drivers of glacial-interglacial cycles for millions of years. These natural cycles have shaped Earth's climate in a slow and predictable manner. However, the current warming trend we are experiencing is unprecedented in human history. The rate of temperature increase over the past century far exceeds any natural fluctuations observed in the geological record. This rapid warming is unequivocally linked to human activities, primarily the burning of fossil fuels, which release greenhouse gases into the atmosphere. These greenhouse gases trap heat, leading to a phenomenon known as the enhanced greenhouse effect, which is causing our planet to warm at an alarming rate. Unlike the gradual changes brought about by Milankovitch cycles, human-induced climate change is happening on a much shorter timescale, with potentially catastrophic consequences if left unchecked. To achieve climatic extremes such as an ice age or a warm period, the settings for these cycles would need to align in specific ways, based on the cycle's durations: eccentricity, 100,000 years, axial tilt, 41,000 years, precession, 26,000 years. The next alignment that could potentially lead to an ice age or a warm period would depend on the synchronization of these cycles. Historically, ice ages have occurred approximately every 100,000 years, suggesting that the cycles align in a way that promotes cooling roughly on this timescale. Given the current settings and the ongoing trends, the next ice age could be expected in about 50,000 years, when eccentricity is high, axial tilt is low, and precession aligns to place northern hemisphere summer at aphelion. Similarly, the next warm period could occur when eccentricity is low, axial tilt is high, and precession places northern hemisphere summer at perihelion. This alignment is less predictable but could occur within the next 10,000 to 20,000 years. However, it's important to note that human-induced climate change is alleged to be currently the dominant factor influencing Earth's climate, potentially overriding these natural cycles. Average global temperature during the last glacial maximum, about 20,000 years ago, was approximately 8 degrees Celsius, 46 degrees Fahrenheit, which is about 6 degrees Celsius, 11 degrees Fahrenheit, cooler than the 20th century average. The average temperatures in polar regions were significantly lower, often below -2 degrees Celsius, 28 degrees Fahrenheit. The temperature differences between the minimum and maximum temperatures were more pronounced due to the extreme cold in polar regions and relatively milder temperatures in the tropics. Medieval warm period, which lasted from about 950 to 1250 CE, saw regional variations in temperature. In the North Atlantic region, temperatures were relatively warm, but global average temperatures did not exceed those of recent decades by much. The current global average temperature is around 14 degrees Celsius, 57 degrees Fahrenheit, with significant regional variations. The differences between minimum and maximum temperatures tend to be less extreme compared to ice ages. The difference in average global temperature between an ice age and a warm period is approximately 6 degrees Celsius, 11 degrees Fahrenheit. During ice ages, the temperature differences between regions were more pronounced, with polar regions experiencing much colder temperatures compared to the tropics. So, in general, the ice age extreme is more extreme than the warm period extreme, if that makes sense. Earth's climate is a complex and interconnected system influenced by both natural and human factors. Milankovitch cycles provide a crucial framework for understanding the natural variations in Earth's climate over long timescales. By studying these cycles, scientists can gain insights into past climate changes and improve predictions for future trends. However, the current rapid warming driven by human activities underscores the importance of addressing anthropogenic factors to ensure a stable and sustainable climate for future generations. But in the long run, no matter what we do, we cannot change the Earth's eccentricity, obliquity, or precession. In other words, the resistance is futile. Just live and love. Be in harmony with the nature and beings around you. Enjoy the experience of life.